and b is equal to 5. So 2 plus 5 is equal to 7. Question, is 2, 5, and 7 are part of real numbers? Yes. So therefore, that is only one of the examples. Another example is 1 plus 2. 1 plus 2 is equal to 3. So that's another example. Let's have another. 3 plus 4 is equal to 7. So as you can see, we can give many examples as we could. But you cannot stop the point that there are a lot of examples, except that you are tired already, and there are still many examples that we can create from this particular mathematical concept. Yes? Math is a universal language. So when saying math is a universal language because mostly, or if not all the disciplines have this, in each discipline it has these numbers. So like for example, sciences. Sciences, we have the chemistry, we have the social science, they need numbers. Okay. Businesses, we know that finance are numbers. Music, the
Ma'am, even government.
I'm sorry.
Even the government po.
Yes. Remember that in the government, we have our connections, the influence. So the politics have, the politics, yung social network, has mathematics in there. Okay, yung pyramid type. Okay, how far is your influence? The election, in terms with respect to the government predecessors. Okay, so it's measurable. The poverty line, economic, how do you call this one, the status, or the, how do you call this one, acceptance of the leadership. Like for example, remember we have SWS survey. So remember, there's numbers. So there is mathematics in there. Okay, architecture, yes, and arts, of course, a lot more. So every discipline there is mathematics. That's why math is a universal language. So in this one, we have expression versus sentences. Word descriptions are translated in mathematical numbers. So the following descriptions are translated. So here is what we call the mathematical. These are the word descriptions, and these are the mathematical translations. As you can see, one mathematical translation have a different way of word description. Okay, so like in sentences, one particular thought can be given or can be expressed in many ways. But we just make sure that the thought should be the same as expressed in different ways. Okay? So here we have A plus B, so there are many, how I've given just only four here. Four ways to express A plus B. And so on for this table. So, for example, you are asked to represent in symbol each of the following. So, 5 less x, so that means 5 minus x. Twice a number decreased by 7, that is, let's say the number is x, so 2x minus 7. A simple fraction whose numerator is y, so the particular variable is y, so you cannot assume any because the variable to be used is given, and whose denominator exceeds numerator by 2. So that is simply, if we're going to write that is y, that's your numerator, and denominator, it only exceeds by 2. Your denominator exceeds by 2. So we have y over y plus. And the number q is 48 less than x. The difference of two numbers is 45. What is the large number if x is the smaller number? So here, we can see that after some executions of the operations, we can get that q is equal to x minus 48. Q is 48 less than x cubed is 48 minus x. So since we cannot find it, but we are just representing the value of the larger number in terms of x. So an expression is a correct arrangement of mathematical symbols used to represent a mathematical object of interest. An expression does not state a complete thought. So there are many types of expressions like constant, arithmetic expression, rational expression, and a lot more. So examples of these are, so these are examples of this expression. So what is a mathematical sentence? A mathematical sentence is a correct arrangement of mathematical symbols that states a complete thought. So this time, if it's a complete thought, then it could be either, the validity is either true or false. So examples in this is 1 plus 4 is equal to 5. So here there are two sides of this particular equation. So that we have the left-hand side and the right-hand side. Okay? In order to make it true, obviously from the bridge, which is known as the equality, the left-hand side should be equal. Okay? So we know that 1 plus 4 is 5. Therefore, the left-hand side is equal to your right-hand side. So this is true.
True.
Next is 10 is the square root of 100. We know that the square root of 100 is 10, right?
Yes.
Actually,
Yes.
the square root of 100 is positive negative 10. But the principal root is positive 10. Therefore, this is true. Next number, 10 is less than 9. So we know this, self-explanatory, this is false.
False.
10 is an even number.
True.
To make an even, just simply divide the given number by 2. If you can get a whole number without a remainder, then it is an even. So let's try. 10 divided by 2 is 5. Therefore, it's an even number. True. So 10 is a multiple of 5. If I will do multiples of 5, starting from 5. So we have 5, 10, 15, 20. So I pass by 10. Therefore, 10 is a multiple of 5. This is
True.
Next, we have the sets. A set is any well-defined collection of objects. Capital letters are normally used to represent sets. And the objects belonging to a set is what we call elements. So there are two ways to write a set. The first one is the rooster method. In the rooster method, you simply write the elements, or that is listing of the elements. So for example, set A is the set of Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. The other one is using the rule method. In the rule method, you are simply identifying what is the thought or the property being listed. So as far as we know, this is the set of days in a week. So using the rule method, set A is the set of days in a week. And lastly, we have the set builder notation. In the set builder notation, we're just adding this variable. So it's the same as the rule method, but this, of course, there's always a, how do you call this one? A revision or modification. So set A is the set of all A such that A is a day of the week. Okay, so we know the day of the week, that those are. So these are the A's now being represented by the set builder notation. Next, we have the cardinality of sets. The cardinal of a set is the number of elements in the set. Any repeated element is counted 1. A finite set is a set with a definite cardinal number. while an infinite set is a set that has no exact cardinality. A unit set has only one element, and a set without an
Oh,
element or zero element is what we call empty set or null set. So let's have an example. A is the set of all x such that x is the day of the week. What's the cardinality of set A? So here, we know that there are 7 days in a week. Therefore, this is a finite set. The cardinality is 7. Next is B is the set of all x such that x is a counting number. If I will try to start listing the counting number that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on, I will write there a 3 periods known as ellipses because I know there are still numbers that follows after my last number. Therefore, in that thought, this is what we call the infinite set. You know that there is a number, but there's no exact number of that. But we can count. But we don't we cannot stop because it's a continuous. So that is a infinite set. Number three, let E is the set of all y such that y is an even prime number. If I will start writing the prime numbers that it start with 2, 3, 5, 7, 7, 11, 13, 17, 19, 23, 29, and so on. So as we can see, or even if you're going to check it, there is an only one even prime number, and that is 2. Therefore, the cardinality of E is a unit set, meaning it has only one element. Let F be the set of Y such that Y is a year with more than 366 days. In the ordinary years, we have 365 days, and during the leap year, we have 366 days. Therefore, we don't have a year with more than 366 days. So the cardinality of F is 0, meaning this is a null set. Next, we have here the set relationships. So sets with the same number of elements are called equivalent sets, and sets with the same elements are called equal or identical sets. For example, if A is the set A, B, C, and B is the set 1, 2, 3, then observing it, the elements are not the same, but the cardinality or the number of elements are the same. Both have 3. So therefore, A is equivalent to B. A subset is a portion of set. This is written as M is a subset of P. The power set of a set A, denoted by this notation, is the set containing all the subsets of A. And the universal set, denoted by U, is a set containing all the elements being considered in a particular discussion. If we're going to draw that, assuming using the Venn diagram, this is our universal set. Let's say this is your P. Where should be the M? M should be inside your P because it's a subset. So this is the M, the small circle. This is your P, and this is your universal set. To illustrate the power set, I have this example. So for example here, okay, let's say given X is the set ABC, Y is the set ABCDE, and W is the set
Of A, B, D, E, C.
A, B, D, E, C. Okay, so what are the relationship existing? Okay, so in here, looking at set X and set Y, I could say that A, B, C is inside the Y because Y has A, B, C also. So therefore, X is a subset of Y. So I could see also that X is inside W, A, B, C. Therefore, X is a subset of
W.
W. Comparing Y and W, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. But they are the same exactly elements. They have the same exact element. So these are equal sets. Y is equal to W. So how many subsets does a subset with two elements have? So we have here a table. So let's say a set is a null set. A null set doesn't have an element. So therefore, the subsets are, we are counting the number of subsets without element. So that's only 1. So we have here 2 raised to 0 is equal to 1. Take another set. Let's say we have here a set. This is a unit set. A unit set has only one element. What are the subsets? The subsets are the sets with first no elements, that is the null set, with one element, that's only one, which is the A. So how many subsets do we have now? So we have 2, 1, 2. So 2 raised to 1 is equal to 2. So let's say we have a set A comma B, and it has 2 elements. So we have here the cardinal number, which is 2. So how many subsets do we have? Okay.
4.
So count the subsets. How do we get 4? So first, look at this one. How many subsets with no element? 1. Because we know that empty set is always a subset of any set. And then how many subsets with one element does this set have? So there are 2. That is A and B. And then, how many subsets with 2 elements does this set have? Only 1. So, adding them all together, we have 4. So, what if we have 3 this time? Let's say 3. So, we have A, B, C. So, what are the subsets? We know that if we have 3, then the cardinality is 3. Okay, so what are the subsets? Okay, so the subsets are, first one is the empty set. Okay,
24.
without element. Okay, count the subsets with one element. So that is A. Next we have B. We have B. Next we have C.
27.
So we have here, we have empty set. And then we have A. We have B. We have C. A, B, and C are subsets with one element. And then let us look for the subsets with 2 elements. So we have,
A, B.
so this is A comma B. Then we have
A, C.
A, B, C. So practically speaking, to make it systematic, we have A, B, A, C, and B, C.
BC.
So A, B. So we have B, C. Oh, I forgot. A, C.
A, C.
And then
1.
look for the subset which has 3 elements. Exactly the given. So we have A,
4,
B, C.
5, 6, 7, 8.
And then count the number of subsets now that we have listed. 1,
9.
2, 3, 4, 5, 6, 7, 8. So that is 2 raised to 3. So 2 raised to 3, that is 2 times 2 times 2, which is equal to 8.
Operation.
Set operations. So we are now on the set operations. The union of two sets, let's say A and B, written as A union B, is the set containing the combined elements of A and B. The intersection of two sets written as A intersection B is the set containing the common elements of A and B. So the complement of a set written as A prime or A complement is the set of all elements in the universal set as not in A. To illustrate this one, so this is our universal set. So let's do the A union B. If the two sets are disjoint, meaning hindi nag-overlap, then we can simply shade A and B. This is using through the Venn diagram. How are we going to illustrate for the intersection? So for the intersection, so if we have two sets, let's say E and B, this time they are overlapping. The overlapping part is what we call the intersection. So this is the intersection, the common. And to illustrate the A prime, so this is our universal set. And let this be the set A. So the A prime is the elements outside of A, but inside your universal set. Okay, so those are the illustrations using the Venn diagram. So example, if A is equal to 1, if A is equal to the set 1, 2, 3, and B is equal to
3, 4,